Welcome, everybody, to my Physics Lab 3 report on the black holes and orbits in this experiment. The black hole simulation code is on the top left, while the spaceship simulation code is on the top right. The purpose of the lab is to study the motion of different objects in space and how their initial conditions affect their overall results. We will create two simulations using fundamental physics principles. The first simulation will be a star orbiting around a black hole, and we will use to predict the mass of the black hole. The second simulation will be a spaceship interacting with a moon orbiting around the planet, and we will use this simulation to figure out the initial speed of the ship to orbit these celestial bodies in a figure-8 orbit. The fundamental physics principles used are as follows. Newton's second law, which is F net equals change in momentum over change in time. The critical part about this equation is that the force depends on mass and change in velocity, as you will see later in this slideshow. The universal gravity principle will also be used, being force equals big G times the mass of the source times the mass of the system over the distance between the source and the system squared. This is important to use in this situation as the force of gravity between two objects in space is different from the force of gravity on Earth. So we can't use force equals mass times big little g. And big G is just another universal constant. The system in the black hole experiment is the star, while the system in the rocket experiment is the spaceship. The surroundings for the black hole experiment is the black hole, while the surroundings for the spaceship experiment is the planet and the moon. The net force of is basically the sum of all forces acting on our system, being the star and the spaceship. The velocity update and position update formula will also be used to aid in our simulation, basically predicting the velocity and position of each object in our simulation after each time interval. In the black hole experiment, we want to know what the difference is between the net force and the change in momentum and their components. Well, in the black hole experiment, there's only really one force acting on the system, being the centripetal force or gravity. The difference between the net force and rate of change of momentum is that one makes the motion happen while one describes the motion. Net force basically makes the motion of the object because of the attraction force between the object and the source. The black hole is basically attracting the star and making it move closer and sometimes even farther from the black hole. This is different from the change of momentum, which just describes the motion, being that the polarity moment describes the speed of the object if it's slowing down, and even if it's going in the opposite direction, while the rate of change of momentum describes the change in direction of the motion, being if it's turning left or right. This is the same for the spaceship experiment. And as even though the spaceship experiment, the planet and the moon are acting on the spaceship with some gravitational force, the net force and the rate of change of momentum are describing the similar things as in the black hole experiment, being that the net force is basically making the motion happen, while the rate of change of momentum describes the motion. What if there was a universe where the black hole, a star, a planet, and a moon existed in this way the simulation was doing? Well, to calculate the motion in a simulation of all these objects, we would need to know the dominant force acting between each of them, which is just universal gravity. And now, while each object would feel the same force due to Newton's third law, the change of momentum between the objects would differ, or change in velocity. This is because change in momentum is relative to mass and change in velocity, meaning that objects with higher mass would have little velocity, while objects with least mass will have greater velocity. The results of the experiment are as follows. The mass of the black hole found was 1.62 times 10 to the 4th kilograms, while the initial velocity of the spaceship was 2.3 times 10 to the 4th in the x direction, 2.5 times 10 to the 4th in the y direction, and 0 in the z direction, meters per second. The spearmint of a black hole looks like this. The green is the star's trajectory, yellow is the star, the black hole is in the black, and gravity is pointing towards the black hole. That's the gravitational force acting on the star. The experiment for the spaceship is as follows. The planet is the blue dot, the moon trajectory is in cyan, and the ship trajectory is in pink. The code for the black hole is as follows. Here we have our initial conditions, our programs which involve Newton's second law mostly, and the final programs which just draw the arrows. The code for the spaceship is as follows. We have our initial conditions, the programs which mostly involve universal gravity, and finally the final programs, which just basically make the motion happen in the experiment. Sources of error, there are really no sources of error in the procedure, as this lab is a simulation. However, in terms of result, this simulation is not accurate to actual movement of planets, as there are more objects in space acting on systems that we are studying. Thank you.